Okay, so let's continue our coding, and so you see what the coding involves, right? So you have the storage and you have to pull it from storage, pull what you need from the storage, do the processing and push it back into storage. Okay, so that's how the storage operates. You need to adjust these lengths and all that, this 2 power n minus depth and all that enters the picture. It's not very difficult to do, as we can see. Of course, there are many more efficient ways in which this can be done. I am not focusing on that. So next is when the state is at when the node state is at 1, which means the left is already done, okay, and it is receiving the decisions. Okay, so if you remember, this u will flow back also, okay, and one needs to remember that also. Okay, so because that's important, I did not have the storage for the u cap, and that's also the same as this. Okay, so the beliefs, and then I'll have the u cap also. Okay, so once again let me emphasize where this is coming from. Okay, so this is the decoder. You remember this decoder, right? So we stored the incoming beliefs. Now what about the decisions that are flowing back? Okay, those also need to be stored. Okay, and you have to store them and then process them later also. So you have to keep them. So for the beliefs, for the decisions also, we'll use the same sort of a array structure as we used for L. Okay, we had L as a big array which stored all the beliefs. Likewise, we will have u cap as the array which stores all the decisions that are flowing back. Okay, and the position is exactly the same as L. Wherever you computed the L's position, the same place you will put the u position also. Okay, so that's the idea. So maybe I'll go back to this thing and show you how I organize the L. You remember how we organized L, right? So same way we'll organize the u cap also. The same way in which, so the same way for u cap also. Okay, repeat for u cap. Okay, so that's what I'm going to do. So let me not spend too much time on it. We can start coding. So u cap is like that. Okay, so u cap comes into operation when you either make a decision at the leaf, right, or you do a step u, or even a step r, right. Even in step r, the incoming u cap from the child node is used. Okay, so maybe I'll start with what happens at depth n and how u cap is used here. Okay, so at depth n, I'm going to check if node plus 1 is frozen or not. Okay, so how do I check if node plus 1 is frozen? There is a command you can use here, any of f equals node plus 1. Okay, so this is node frozen. Remember, I am at depth n, I am at the bottommost thing. Okay, so I am at the bottommost. At the bottommost, it's easy to address the position in the u cap array. If it's frozen, u cap, so I'll just explicitly store u cap to be 1, node plus 1 equals 0. Okay, so in the bottommost, you have the entire length coming in. Okay, and then every node is just one position away. You don't have to do any calculation for the position. That's one thing nice. So here, if so this is the decision, right? So if L of n plus 1 comma node plus 1 is greater than 0, greater than or equal to 0, u cap of n plus 1 comma node plus 1 equal to 0, else u cap of n plus 1 comma node plus 1 equal to 1. There it is. So that's the decision. Okay, so once you finish the decision, you're not done. You have to hand over to the parent, right? So how do you hand over to the parent? I do node equals. So one thing you can do is you can check if this is the last one. If node equal to n minus 1. So if you have made a decision on the last node, you can set done equals 1. Else, if you're not done the last one, you can make node as floor of node by 2. Okay, so this is my flooring, and then depth is depth minus 1. So, you proceed further. Okay. So, this is going off to the next one. I am not going to bother too much about the changing the state of the leaf node, okay, because it is not so important. Once you get there, you decide and you go on. Okay. So, this is what the leaf node does. Once you come to the leaf node, it will go through. Okay. So, in fact, we have done enough so that we can even simulate and see whether things are happening correctly or wrongly. It's not too bad at this point. I believe you can go up to some point, because so remember, you do a lot of down steps initially, and then you make a decision. Okay, and then we can avoid the work in progress quite a bit if you do this. So, let's I think it's good at this point to run it and then see what happens. So, let me come up to this point and set up a breakpoint here. Hopefully, it will run, and let's run. Okay. So, when you run it in debugger mode, we have to go back to the, okay, so that we see that the decoder is here. Okay. So, we have done, and this is started. Remember, our starting point was, this is n equals 16, right? Yeah, 16 and 10. So, maybe we can see the frozen position just to be sure. 1, 2, 3, 5, 9, 4, it's okay. So, that is the frozen position. So, let us start going in. Okay. So, we step here, and node and depth, this should not happen, it is not a leaf. Okay. And then it is calculating the position, depth is 0, node is 1. So, n pos should work out as 1. So, this is a way to, okay, anyway, so I will check it out. N pos is 1, that is okay, and ns of n pos will be 0, no problem here, and you compute temp. Temp will be 16, okay, and then depth is 0, so node is 0, temp is 16, so this will be 1 all the way up to 16. Okay, so ln will be the same as L. So, if you see ln, it will have 16 values, and this is the received values from the channel. Okay, and then you store temp by 2, A and B. A will be the first part, B will be the second part, and then you go to the next node. Node is again 0, but depth is 1, okay, and temp has become temp by 2, and then you do the storing of L. Okay, so let us see L of 1 comma 1 colon 8, right. So, this is what I will know. The remaining will actually be 0 in L. So, we will just do this, and how do you see this? So, maybe we can see this a little bit better if we do this. So, we can see A, we can see B, and then we can see L. Okay. Maybe we can see all. Oh, okay. So, this became a bit ugly. So, let us see A, B, and then L of 1 comma 1 colon 8. Okay. So, you can see that the min sum is working correctly. So, you see the min sum is working not so correctly. Why is that? Oh, okay. So, I think so something is wrong with this min sum. I do not know why A and B together should give you this, because this min sum is supposed to be minus 0.2, isn't it? So, something is slightly wrong in my f construction. So, let me just check this out. So, if I do f of 2.7 and minus 0.2, I should get minus 0.2, but that seems to be working okay. But f of, let me check this, minus 1.7, 2.7, comma 1.79 minus 0.2. Let us see. This is also working out okay, but oh, okay. So, I think I know what mistake I made. This is L of 2 comma, okay, sorry, okay. So, I was right, the program was working correctly, I was just not checking the correct L. It needs to go to depth plus 1, right. So, the next storage, so incoming in the next node, and that is coming out correctly. Okay. So, it is the min sum, you can see the product of the signs and the lower of the two values being retained here. Okay. So, this is the belief here, and the state goes into the next one. Okay. So, that is the end. So, if you want, you can see the node states, be a big matrix, but the first one alone is 1. Okay. So, the next one, in the next step you don't have this, but then if you look at npos will be 2, I think. Okay. So, that is the correct npos, the second position, and then again it will be 0. Okay. So, again it will do this will work out hopefully correctly. Temp will be 8. Okay. And then ln will have pulled out correctly the values that we had. You can see L of 2 comma 1 colon 8, that agrees with what it pulled out, and then you do the same thing as before, A, B, and then you go to the next node, temp becomes 4, and then you do L. Okay, and then you set it as npos. So, if you now look at L, you will see this big matrix. Initially there were 16 values, then you had 8 values, then you have 4 values. Okay, and then this 4 values you will see are the min sum of these two, and you will proceed like this. So, you can go up to the leaf node actually. So, you go to the next depth, again the same process continues. Okay, so you can see L. Okay, you come up to these two. Now we are at the depth of 3, so we are almost at the leaf node. Then we can do one more. You are at the leaf node now. Okay, so you can look at L. You see this triangular sort of structure, right? 16, 8, 4, 2, 1, and this is your belief for the U1. Okay, but interestingly, U1 is I think frozen. So, if you have depth n, it is frozen, and then you totally ignored it, but still it is okay. Node is not n minus 1, and then you go to the next node. Node is still 0. You have depth 1. Okay, so you have come up to the next one depth higher. Okay, and here if you do, it is not a leaf node. Okay, you got to the right position, but now ns of npos will be 1. Okay, and we have not written code for it. So, let us start writing for that. Okay. So, hopefully you saw how the decoder was working. It gave you an idea of how these things work, how the traversal happens. So keep that in mind. So it goes left, 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 and then it made a decision, and it wanted to go right, but we haven't written code for going right. So, let us try and do that now. Okay. So, once you have figured out how to write for left, the right is also not very difficult to write down. So, I know this. So, I will again start with the same sort of logic. I need the incoming ones, I need the split. Okay. I need to know the next node, I need to know the next temp. Except for this, everything else will be the same. So, I can do a cut and paste here and then modify. Okay. So, you will see there are few changes we have to make here, because the state is different. You also need like ln, you also need the, so we got the incoming beliefs split and all that, that is good, but we also need the incoming message, right. So I am in state 1. Okay. So, if I am in state 1, it means my left child is giving me something. Okay. So, you have to go to the left child and pick up the u cap from the left child. Okay. So, that is what is important. The left child's u cap is what you have to pick up. Okay. So, what is the left child? You are at node and depth. So, the left child is 2 into node, and the left depth is depth plus 1, right. This is your left child's coordinates, so to speak. Okay. And then once you do that, you can have an L temp, which is 2 times 2 power n minus L depth. Okay. And then you can pick up u cap of the node, okay, the incoming message from the left child, which will be u cap of L depth plus 1 comma L temp into L node plus 1 colon L temp into L node plus 1. Okay. So, this is incoming decisions from left child. Okay, so hopefully this is clear to you. Remember, when you do the G function, you not only need the incoming beliefs, you also need the incoming decisions from the left child. Okay, so you have to compute who your left child is, go access the corresponding storage for UCAP, and pull out the storage. Okay, so for some reason it's warning me that I didn't do something correctly. I think I didn't close the brackets. Okay, so that's it. So once you do this, then you go to the next node. Now next node has to be the right child. Okay, the right child is the node into 2 plus 1. Temp still goes down by 2. Okay, then you go to the right child. So now you can do A, B, and then U cap M. Okay, so this is G and storage, and now you can make the NS as 2. Is that okay? So maybe a little bit inefficient, but I think we managed to do the right thing as well. So let's code up even the step U, which is going back up to the parent. So so far so good. We have not done anything too wrong. So let's do going up to the parent. Going up to the parent is actually also very similar to this in some sense. So in fact, here even for the L temp, I don't think I need. So since L depth was just depth plus 1, I can simply say temp. L temp is temp by 2, I think, right? So when you go to the left child, L temp becomes temp by 2, just to avoid a little bit of computation there. Okay. All right. So this so let's figure out what to do when NS is state is 2. Okay. So when state is 2, what you need to do is compute temp. Okay, so let's compute temp. That's okay. We do that, and then we don't need A or B, but we need the U cap N from the left child. Okay, left node is this, left depth is this. Okay, so I'll call it C depth because that is the child's depth, and then C temp, which is the child's temp. Okay, and then U cap left is U cap of C depth plus 1, C temp into L node plus 1, C temp into L node plus 1. So this is incoming decisions from left child. So I need a U cap R, for which I will need R node. Okay, so I'll put R node also. Right. So so see, this is else I need to do step U. Okay, step U and go to parent. Remember this. So this is step L. This is step R. Okay. So something very similar with U cap 2, U cap R, which is R node. Incoming decisions from right child. Okay. So now we are ready to do step 2, step U, but for step U, you also need the L to come in properly. So that's okay. I think we can do that. So just like this assignment, you have the assignment for U cap. U cap equals, so this is u cap L, we have to do mod 2, right, mod of u cap L plus u cap R, comma 2, and then u cap R. There you go. So, I think that's step U. I think that's correct. Okay. So, once you do this step, you have to go back to the parent, and going back to the parent is it's done here, right. So, floor of node equals floor of node by 2 and depth equals depth minus 1. There you go. That's it. So, so the same steps that we did before, we've implemented, and in fact, looks like we are done with the decoder. We've implemented all steps, but we have to check whether everything is happening correctly or not. We haven't done the debugging part, but as far as the basic implementation is concerned, we are more or less done. So, since we already checked the first initial part going up to the first decision, I'll clear this breakpoint and I'll put a breakpoint here. Okay, so when you have to come here, okay, so when you have to do or here maybe, okay, so I'll put a breakpoint here so that I can run this, and I've done all the left steps, okay, and I've made a decision, and now I have to come back. So, just to show you that all that worked correctly, let's go back and check the decoder once again. I'll clear the screen and I'll show you the L. Okay, so you can see the L, it has come back down to the position here, and you can also see the U cap. It's just 0 at this point. It's no big deal. That's where it is. And now we are ready to check the write operation. Okay, so this point n pos should be 1. Okay, so it's going to go. Remember what is the node and the depth? So depth is 3 and the node is 0. So where am I now? I've come back all the way to the leaf. I've made a decision on the leaf, and then I've come back to the previous depth. Okay, so you remember once again. So maybe I should go back and show you where we are on the graph. We are somewhere here. Okay, so here is where we are. Here is where we are in the decoder. Okay, so we went all the way down, made a decision, and then we came back, and we want to go back here. Okay, so we need to do that operation, and let's check whether that operation is happening correctly or wrong. Okay, so that's where we are. Step R and going to right child. Temp, that should be okay. ln, that should be okay. A and B, that should be okay. And then it finds the left child, that should be okay, and the left temp, and then the U cap n, it should be okay. So let's check if all those things happen correctly or not. Okay, so this A and B have to be just single values. Okay, and these should just be this 0.51949 and 0.3740. Okay, so that should be the A and B, and U cap n must just be 0. Okay, so it should be 0. It would have picked up the correct U cap n. Let's assume it did that. Okay, this U cap n, it would have picked up. Okay, so that's okay. If you want, you can go in and check it, but I think it's okay. So then it did all that, and then it's going to the next node. Okay, so if you look at it now, node will be 1 and the depth will be 4. Okay, it's gone to the next node. Temp probably was 2, so temp needs to go back to 1. Okay, and then you need to assign it to the correct L, right? L is, I've put F here, it should be G. Okay, so that's where the error will come. If I run this, there's going to be an error, so I'll put G here. Okay, so I made that mistake. It should be G. So this will run the correct thing. Okay, so let's run it once again and quickly step through all the way up to here. Things were working correctly, and then this assigned the L for that guy. Okay, so let's see what happened to the L. This happened correctly or not? Yeah. Okay, so this must be just the sum of these two, and you can see 0.33 is correct. Okay, so it added these two, and you got the sum. That's the L value. Okay, so the next step is I've made the state as 2 for this. and see, I'm not bothering once the u happens to change the state, because I mean I could change it, but I won't come back to it ever again, so it doesn't matter too much. And then we continue, and then it will go to decision. Okay, so it will make a decision. It's frozen again, and it's not so. It goes back up in depth to the next one. Okay, so now it will come to once again. Where does it come? Okay, see, remember it has finished the decision here. It has come back here. Now this node we have to do step u. Okay, so it needs to figure out this step u here, and it will do it. You'll see it does it correctly. Okay, so depth is not n now. So n pos it calculates, and step it's not 0, it's not 1, it will go to 2. Okay, so now it has to do a step 2, calculates the depth, and then the L node and C depth. So let's just check it out once again. So depth is should be 3, node should be 0. It's going to go up, right? So and then let's look at L node. It will be 0 again, and C depth will be 4. Okay, so that's okay. And then it calculates C temp. That's okay. It does that. C temp should just be 1. Okay, you can check that. It's 1. And then it pulls out the U cap, both from L node and R node. This will just be 1 bit. Okay, so U cap L and U cap R will both be 1 bit, and they'll be 0 because they were frozen positions. And then you calculate the U cap for the for going up. Okay, so if you do this, it will again be 0 0. So if you see U cap, I mean everything is going to be 0, so you're not going to see much. And then you go up to the parent. Okay, when you went up to the parent, you would have gone to depth of 2, and the node would be 0. Okay, again depth 2 0, and then after this it will continue. Depth is not n, and calculates n pos. This will be actually 1, so it will do the right calculation. So it's good to check what it did here. So remember, it is going to go right. Node is 1, depth is 3. Okay, so what is node 1 step depth 3? So maybe you can see what is node 1 in depth 3. So it has come here, and node 1 it's come here. Okay, it's come to this guy. Okay, and did it come there? Let me just be sure. Let me just see the L here. Yeah, so this is fine. So it is to go to node 1 in depth 3. Yeah, so I think I went through the L and I just didn't pay attention. Okay, so that's okay. So that's good. So let's check out the A and the B. Okay, A is 2 values now. Okay, so 0.5684, 0.2086. Then B is the remaining 2 values, 0.1285 and 0.4985. Okay, so node, okay, so for some reason I calculated it, I've gone to the next node. Okay, all right, so this is fine. So this is good. So then you have U cap n, which will actually be 2 zeros. Okay, and then when it computes it, it will go off, and then the next state goes to this. So I've not gone to the next node, and that's the next node I'm going to. So now this node is 1 and true. Okay, so this is okay. So this is working correctly. So you have the L's calculated. Okay, so you can go through and look at this and see how it proceeds. And then this will not be true. This will go left further again. Yes, and then it will come back and make a decision, and then it will go right again. Just to check, and then it will go make a decision. It's doing a lot of things. So it seems to be working. There is no major bug here, at least I have not checked it fully, but it at least is working. So I'm going to clear all the breakpoints, and just to check what is happening, so I'm going to print some information out just to check that things are happening correctly or wrongly. So anytime I enter my left, I'm going to print print doesn't work. So I'm going to just display node and depth. Okay, so just to make sure I see something every time I go left, and so I should say I went left, right? So I'll display left also. Okay, then I'll say when I go right, I will display right, just to see that the whole thing is proceeding correctly or wrong, and then depth and node and depth. Okay, just to see how the whole thing is going. Then it should finish. So let me just run it once to see what it does. Okay, so it finished. It gave me some answer. I have no idea whether the answer is correct or wrong, but at least it ran. So let's see whether the sequence is correct or wrong. Okay, so that's the first thing one can check. L node 0. Okay, so it went left to depth 1, went left to depth 2, went left to depth 3, and then it went right, okay, to depth 3, right from depth 3, and then right from depth 2, left from, so it looks okay, and it has given me some final answer. So you can check on UCAP N. So if you look at the UCAP, this is the overall UCAP, but remember the actual message is in the last row. Okay, I didn't pull it out in the code, but the actual message is in the last row. I was just checking here to ensure that everything is happening correctly. It looks to be working fine. So the actual message is in the last row. Okay, so let's maybe not print these things. This is just some debugging to check everything is working correctly. It seems to be working correctly. So I'm done with the decoder. So now I can assign my MCAP, right? So my actual so I have to pull out the messages from the frozen positions, or I could just compare the UCAP of the last one with the U, right? So U is my actual code word, or the code word itself. So that is something that one can do. Let me save this. Okay, so you can see if these two are equal. So the message went into U of this, right? So this is where the message went into. Okay, so if I pull out this, I should get the message cap back. Okay, so let's do that. UCAP of n plus 1, comma, the same Q1. Where was this? Q1 of n minus k plus 1 colon n. Okay, so this is the position where the thing got inserted. So the same thing in the last row should be my message cap. Okay, so let's run this and then see if at this high SNR if it's working or not. So you had a message and you had a message cap, and they are the same. Very nice, isn't it? So it's good to see that the message and the message cap agree. Maybe there were no errors in the channel, but still our decoder is working and it is agreeing. So you can again do the same thing as before, our way in which we count the errors. You remember, I do the error counting. Okay, so we can do that. Okay, so I'm not putting it in a loop, so this part is not so relevant, but anyway, so I'm not putting it in a loop for calculating the message and sending it out. So maybe that part we can add. Okay, so how do you add that? So you put this here, n blocks. Where do I put this? I need it below this. Simulate and then I need a for loop, and the for loop needs an end, and the whole thing can be indented a little bit so that it goes off correctly. Okay, so I think I've done most of what I wanted to do. So I put block error 0, and then I'm simulating for every block, and every block I generate a message, I add code word, then I transmit it, I assign these things to 0. I think I'm doing all of that correctly. Then simulating it, decoding it, getting the message cap, and checking it up. Okay, and then we can now print the brsim and this. There you go. So this will even simulate 100 blocks for the 1610 code at a 4 dB SNR. So let's do that. There you go. Okay. Did I not put an underscore? Okay, sorry. There you go. Okay. Forgot to change the capital K. Okay, so now we're ready to simulate, and you get some answers. Okay, so there were 3 block errors out of 100. Format short G. Oops, what did I do? So one can decode. So you get 2 errors out of 100, 3 errors out of 100. So this is basically working. So maybe we want to be more experimental. So let's try the largest block length that the 5G standard allows, 1024 and 512. So this is going to be big, and let's see what it does. No errors. Okay, at 4 dB is huge SNR. So let's make it maybe 1 dB. Maybe we'll see some errors. Out of 100, 78 were in error, so maybe 1 dB is not too great, maybe 2 dB. 11 were in error, so on. So the basic decoder, I believe, is working. This is the successive cancellation decoder for polar codes, and you saw it's reasonably easy to code. It's a short piece of code that gives you good answers. Okay. Of course, one can make it more efficient, one can make it more interesting, one can make any more modifications. We can keep on working on it. But what we will do in the next week is to look at list decoding for polar code. So list decoding is quite important. That is the decoder which actually works in practice. It gives you better gains than this. We'll see that in the next class, in the next lecture. And as far as this lecture is concerned, we are done. Thank you very much.